So this will be an introduction into pH and buffers. Now, all solutions are made up of acids or H3O plus ions and basic ions, OH minus ions. And neutral solutions have equal amount of H3O plus ions as well as O minus ions. And that concentration is equal to 1.0 times 10 to the minus 7. In an acidic solution, you will have larger H3O plus ion concentration than OH minus concentration. So in acidic solution, H3O plus ion concentration is always greater than 1.0 times 10 to the minus 7, while OH minus concentration is less. In a basic solution, you will have a larger OH minus concentration. So for basic solution, the concentration of H3O plus ions is always less than 1.0 times 10 to the 7. Now, we measure acidity using the term pH. pH is equal to the negative log of H3O plus ion concentration, or H3O plus ion is equal to 10 to the minus pH. Now, as seen earlier, neutral solutions have a H3O plus ion concentration of 1 times 10 to the minus 7. And so the pH of water is equal to the negative log of 1 times 10 to the minus 7, which is 7. So the pH, if pH is less than 7, then the solution is acidic. If it's greater than 7, then the solution is basic. If the pH is equal to 7, then that solution is said to be a neutral solution. The pH scale is a measure of acidity or basicity, and the normal range of the pH scale is from 0 to 14, where a pH of 0 is equivalent to 1 molar solution of HCl, whereas a pH of 14 is equal to 1 molar sodium hydroxide. Now, if you look at the pH of our stomach, we can see the pH of our stomach is between 1 to roughly 3, whereas, say, the pH of cherries is about 3.2 to 4, and the pH of or normal body pH or blood pH is between 7.3 and 7.4. At pH 14, you're looking at a 4% solution of sodium hydroxide. Now, when you find pH, you can also find the pOH, which is basically another way of expressing acidity or basicity. So the pOH is equal to the negative log of the OH minus concentration. So in this case, you must know the OH minus concentration in order to determine the acidity or the basicity. So similarly to pH, the pOH of water is equal to 7. Now, the pH-pOH relationship is defined by pH plus pOH is equal to 14. So in a solution where you have the concentration of H3O plus and OH minus, we call that solution Kw, and Kw is equal to 1 times 10 to the minus 14. And this is why pH plus pOH is equal to 14. Now, pKa is a measurement of how strong an acid or base is. So pKa is negative log of Ka which we described earlier as the acid dissociation constant. And so the stronger an acid, the smaller the value of the pKa. Similarly, we can measure pKb, which is negative log of Kb, and of course Kb is 10 to the minus pKb. And again, the stronger the base, the smaller the pKb. Now, pH is important in our environment. One of the most important reasons is because of acid rain. Rainwater with a pH lower than 5.6 is called acid rain. And if you take a look at a map of the United States, you can see the areas in which we have this acid rain. And acid rain has been linked to a lot of changes in our natural ecosystem. And you tend to see acid rain in more industrialized areas of the United States and everywhere throughout the world. So, acid rain is a result of the interaction between the atmosphere with certain pollutants that are found in the air, such as carbon dioxide, sulfur dioxide, and nitrogen dioxide. So in the air, these oxides react with water to form, in the case of carbon dioxide, carbonic acid, and in the case of sulfur dioxide, it forms a sulfuric acid, and nitrogen dioxide would react to form nitric acid. And these are all pretty strong acids. So increase in the acidity of rain is caused by various processes, some of which are natural, such as volcanoes, some of which are man-made, such as combustion of fuel. Now, acid rain is bad because these acids react with metals and materials that contain carbonates, and they'll dissolve them. And they also damage or bridges or cars or other metallic structures that they come in contact with. Acid rain also damages buildings that are made of limestone and cement, and it will acidify our lakes and affect our aquatic life. And again, it will cause a dissolution of minerals and leaching minerals from the soil, making it more difficult for trees. Buffers. Now, buffers are solutions that resist changes in pH whenever an acid or a base is added to it. They can contain either a significant amount of a weak acid and its conjugate base, or significant amounts of a weak base and its conjugate acid, depending on what you would like the system to buffer. The blood is a mixture of carbonic acid and hydrogen carbonate. So here we form a buffer by reacting acetic acid with sodium acetate. In this solution, you will now have acetate ions, acetic acid H plus ions, and sodium ions in the solution. So once you add a strong base to this buffer, it is neutralized by the acetic acid or the weak acid that is found in the buffer. So imagine sodium hydroxide being added to the system will react with the acetic acid to form water and sodium acetate. On the other hand, if you were to add to the system a strong acid, then it is going to be neutralized by the original weak base that we added, the sodium acetate that is in the buffer. And this is explained by the reaction, for example, adding HCl will react to form more acetic acid as well as sodium chloride. And hence, the pH of the system is maintained whether you add acid or a base to the system. Now, a good buffer is able to neutralize moderate amounts of acid or base. However, there is a limit to how much can be added before the pH changes significantly. This is called the buffering capacity, and it is the amount of acid or base that a buffer can neutralize. Now, buffer also has specific ranges in which it will operate. And the buffering range is the pH range that a buffer can be effective. And you design your buffer for this. So the effectiveness of a buffer depends on two factors. One, the relative amount of acid and base that's in the buffer, as well as the absolute concentration of acid and base. A buffer will be most effective if the ratio of base to acid is equal to 1. It will also be most effective if the acid and the base concentration are large. So those are the conditions under which a buffer would be most effective. But a buffer will still be effective if the base to acid ratio is about less than 0.1 to a ratio of less than 10. It will still be an effective buffer. It won't be the best buffering conditions, but it will still be effective. Titrations are a way of determining the concentration of an unknown solution. We do this by adding the known solution from a burette into a known amount of the unknown solution. We measure plotting a curve which shows the pH value versus volume added gives us an equivalence point, which is your neutralization point. Here we have a strong acid and a strong base type. A plot of the pH versus the volume added yields a titration curve from which you can deduce the concentration of your unknown solution. Equivalence curve depends on the type of acid-base reaction that you are plotting. A weak base strong acid curve is going to be different from a diprotic acid, which will have two equivalence points. However, they can all be used to calculate the concentration of your unknown solution.